Okay, now we are going to talk about acceleration, and we're also going to talk about Newton's three laws, which you might be familiar with. But first of all, when we were looking at velocity, velocity was change in position over time. Okay? So now for acceleration, acceleration is going to be very similar, except it's going to be the change in velocity over the change in time. Alright. And so, with velocity, we were measuring everything in meters per second. Every second you go a certain amount of meters. Now for acceleration, it's going to be meters per second, which is the same as meters per second squared. And so when you do your calculations, we'll always have time squared on bottom and a distance on top. And what this basically means is our velocity is changing every second. If you have an acceleration of 2 meters per second squared, what that means is every second your velocity is increasing by 2 meters a second. And so, if you were to make a table of this quick example right here, let's say after 1, 2, 3, and 4 seconds, well, I should probably also include 0. If you have time and you're looking at velocity, your velocity is going to move from 0 to 2 to 4 to 6 to 8. So you're going faster and faster. This is speed, not position. And because you're going faster and faster, you're going to travel further and further distances. Alright, so there are going to be a lot of examples and a lot of problems where they ask you to find the acceleration or deceleration. So for example, a car brakes over, and I guess without spell check I will use the wrong brake. A car brakes for 4 seconds from 20 meters per second. What is the acceleration? Alright, so acceleration is change in velocity over change in time, which means we're going to take 20 meters per second and divide by the total change in seconds. Change in seconds was 4. And again, right here, you'll see this is meters per second, meters per second squared. So we are going to end up with 5 meters per second squared. But there is one catch here. We are starting at 20 meters per second, and we are decreasing down to 0. The total change in our velocity then is negative 20 meters per second. We have decreased by 20 meters per second that whole time. So this is going to be a negative 5 meters per second squared acceleration. We are slowing down by 5 meters per second every second. So that is a case where the sign does matter. That negative is important because we are slowing down to a stop. Alright, so here are Newton's laws. Alright, number 1. This is inertia. If forces are equal to 0, an object continues at its velocity. You may have heard objects in motion tend to stay in motion, or objects in rest tend to stay at rest. This is what it means. If there are no forces acting on it, if the total forces are 0 like this, an object continues at its velocity. So if it's at rest, it stays at rest. And so you've seen people pulling out the tablecloth underneath all the dishes. Now that trick there happens because objects at rest tend to stay at rest. And when you pull a tablecloth out from under the dishes so quickly, there is no actual resulting force on the the objects that are on top of the table. So their total forces that they're receiving are 0, meaning they want to stay where they are even though the tablecloth is moving out from under them. Okay, so number 2, we will write it like this. Okay. Force equals mass times acceleration. And so this little sigma means sum. It means that we're adding up all the forces together to see the total force that's being acted on a certain object. And so there's this idea that, let's say we have an object here. If I have force 1 acting on it, and then I have force 2 acting on it, there's going to be this result that's an addition of the two. You take force 1 plus force 2 and call that a sum vector, a resulting vector. And so that's why we always write sum here. You look at the total force that's being exerted, and then you look at that vector when you're doing force equals mass times acceleration. The other way the book might write it is that acceleration equals the sum of the forces divided by the mass. And basically, they just divided by m on both sides. But this is how you would find the acceleration if you needed to. You take the force, divide by the mass, and you get acceleration. So force units, the force units are in newtons, in honor of Sir Isaac Newton, who came up with these laws and came up with most of modern physics. A newton is a kilogram per meter, a kilogram times meters over. Let me try this once more. A kilogram meter per second squared. Ugh, what easy for me to say. Okay, and that's because this is mass here. That's your m, and this is your acceleration here. So even though it looks a little complicated, it's not that bad. Another units that you could use is pounds. You could just use straight up pounds. Say like there's a 20-pound force on something, but it's a little hard to do conversions and use that in distances and so on. So we're going to do an example for 2 before we go on to 3 for an example. And let me write this out for you. Okay, an asteroid is pushed by a 6 Newton force. Its mass is 1.1 kilograms. What will the acceleration be? Okay, so we'll just use force equals ma. We know that the force here is 6.0 and that the mass is 1.1, and we're trying to find a. So it's pretty straightforward. You plug it in and then you get the variable you want, a. So you divide by 1.1, and when you take 6 divided by 1.1, you get 5.45 repeating. So what we're going to do is take into account that we have 2 sig figs and 2 sig figs. So I will call this 5.5, because I rounded it to 2 sig figs, meters per second squared is your acceleration. Okay, so that's how you would use the second law, force equals mass times acceleration. And there's one thing to note here. I used pounds up here, but you have to be careful with Newton's force and with mass and with weight. Weight and mass are not the same. And so mass is the amount of stuff in an object, and it's intrinsic. But weight could be different depending on which planet you're on. Weight is when you take your mass and measure it on a scale on, like, the Earth. But if you use that same scale and the same mass on Mars, it's going to be different. So just be careful not to confuse weight and mass. Alright, so number 3 here, third law here. Every force has an equal and opposite reaction. Okay, so here's the conceptual example I have for you here. I have me pushing a gigantic refrigerator along the ground here. If I apply a force, 1, going this direction, there is actually another force that is exactly the same being applied in the opposite direction, force 2, against me. And so with math, we would say force 1 is the opposite, but equal to force 2. And so that will be more important when we go on to talk about more and more of force examples. But every force has an equal and opposite, even if you don't feel it. If I want to be pushing against a wall, I'm pushing really hard against the wall. It doesn't matter if you don't feel it. The force I apply will be equal to the force being applied in the opposite direction. Okay, to recap here, I just want to do a quick review of the formulas you really should know. Like velocity is change in position over change in time. It's also the slope of xt graph. Acceleration is the change of v over change in t, and that is the slope of the vt graph. Lastly, force is mass times acceleration, or it could be written as the sum of the force vectors equals mass acceleration.